Hey guys, welcome to the lesson on combinations and binomial theorem. So this is our second lesson for our probability unit. So given an understanding of permutations, permutation is what we studied the last segment. It was an ordered combinations. So understanding how to count these or use these to count, students, meaning you guys, will analyze combinations and reproduce Pascal's triangle to break down the binomial theorem. So let's go ahead and start with a definition. So combinations. Combinations is a selection of R objects taken from a group of N objects where order doesn't matter. So really, when we looked at permutations, order mattered. Either we were first, second, or third, or to open a combination, it was 3, 3, 3, or 3, 2, 1, or 1, 2, 3, or the license plate example, it was A, 9, 9, A, A, A. So the order in which we gave a combination, by definition, a permutation was an ordered combination. So when we're dealing with these combinations, order doesn't matter. So the way I would think about it is if I collected baseball, well, I did collect baseball cards, we get a packet of 12 cards per little packet. I can pull out 4 at a time to see the cards. Now, I didn't care which 4 I picked. It didn't matter if it was the first 4, the last 4, the middle 4. It didn't matter what 4 I was looking at to begin with. All that mattered is that all I cared about was looking at 4 at a time. So when order doesn't matter, we use combinations. If we look at the definition, or we look at our, I keep wanting to say algorithm, our, if we look at our formula, we notice that we have NCR, or for combinations. Another way to read it is N choose R. So we want to take N objects, choose R at a time. So again, if we think about our baseball example or baseball cards, if I had 12 baseball cards to choose from, or I'm sorry, 12 baseball cards in my packet, how many did I choose at a time? Well, I would choose 4 at a time. And then we would have plugged this into our formula. We have 12 factorial over 12 minus 4 factorial times 4 factorial. So something to keep or something to notice is that we're adding this extra r factorial to our denominator. So we can go ahead and multiply that out the long way. Or what we can actually do is use our calculators. Go to math. We're going to go back to our probability tab. And if we look at the third option, we notice that we have N choose R. We click on that. If I had 12 baseball cards and I chose 4 at a time, I end up with 495 different combinations. So I can view my packet of 12 baseball cards 495 different ways, 4 at a time. So that's with combinations. It's actually I think it's the easier of the two, just because order doesn't matter and you can just calculate it quickly. So an example of this, in our warm-ups, we looked at our playing cards and we analyzed how many suits, and all that good stuff. So here we're going to sum it all up. We have a standard deck of 52 playing cards, has 4 suits, 13 different cards in each suit. So here they are. We have our spades, hearts, diamonds, and clubs. A says if the order in which the cards are dealt with is not important. So I'm telling you that order is not important. It doesn't matter. How many different 5-card hands are possible? So before we even dive in, I want to teach you a neat little trick. If order is important, we notice the word important has that P to it. So when it is important, we know we deal with, NPR. So if it's important, it's NPR. If it's not important, we go NCR. So just kind of to distinguish between the two. So for this one, it's not important. So if we have 52 cards, we're dealing with 52 cards for A, and 5 are dealt. If I have 52 cards, how many of those 52 cards am I choosing to deal? Well, I'm choosing to deal 5. 52 choose 5. So if I were to punch this into my calculator, again, I'm going to use the second enter command to repeat. We get 52, delete, there you go. 52, and I'm going to choose 5. we get that huge number. So that is 2,595,000. I'm sorry, 2,598,960 different combinations. So let me go ahead and move that to the side just so that I can write it in. We have 200. Oh, that didn't work. 22. Well, you get the point. I can't seem to have both these up. So yeah, we get 2. Yeah, so there it is. Cool. So let's go ahead and now look at B. For B, it says, in how many 5-card hands are all 5 cards of the same color? So now we're dealing with colors. Well, how many colors do we have in a poker deck? Here, if we're looking at all of our cards, we either have black or red. So we have 2 colors. So out of those 2 colors, I'm choosing one to stay with. I don't care if it's black or red. I just want to stay the same color, of the same color. So since we're using the word and, I'm sorry, I'm going to get there in a second. And, so we choose one of them. And means multiplication. Out of those, or the single color, how many cards of a single color do I have? I have 26 of them. So I have 26 red or 26 black. So out of those 26, how many am I choosing? I'm choosing 5. So the way we would punch this into our calculator would be, let's kind of clear this up. We have to choose one of those colors. Here's my 1. I'm going to scroll to the right. So make sure you guys get out of the sub index here and scroll to the right. And we have 26. Choose. So I'm going to go to probability. I'm going to choose 5 of those. And these are the different combinations. So we actually have 131,560. So 131,560, I believe. Let me just make sure. Yeah, cool. So there it is. That is when we kind of narrowed down what we wanted. So let's look at example 2. Example 2, or before we go there, there's very important thing that I want to highlight. Understand that when you use the word and, so I'm going to highlight it, and you have to multiply. Anytime we're dealing with combinations and I use the word and. So it was red and all 5 cards, the same. Or if we use the word or, we have to add. So anytime we use and, we're multiplying. Anytime we use or, we're adding. So let's kind of distinguish from the two. If we go to example number 2, it says William Shakespeare wrote 38 plays that can be divided into 3 genres. Of the 38 plays, 18 are comedies, 10 are histories, and 10 are tragedies. So again, I kind of want to underline what is important to me. So here's 38 plays. Out of those, 18 were comedies, 10 were histories, and 10 were tragedies. So if we look at A, it says how many different sets of exactly 2 comedies and 1 tragedy can we read? So exactly, so the key word here is and. So exactly 2. Well, how many comedies do I have to choose from? I have 18 comedies to choose from. I'm going to choose to read 2 of them. And, so there's my multiplication. And, well, there it is. I want 1 tragedy. Well, how many tragedies do I have to pick from? I have 10. I'm going to choose 1. So again, to multiply that out, you can just go on your calculator. And we can do the exact same thing. We go to 18. I'm going to choose to read 2 of them. Now you can also get out of that and put your multiplication sign. And we have 10 tragedies. There's my 10. And we choose to read 1 of them. So I have 1,530 different combinations. So 1,530 different combinations that I can read, or I can read 2 comedies and 1 tragedy. So now let's take a look at B. For B, it says how many different sets of at most 3 plays can you read? At most. So at most means I can be lazy and read none, or I can read 1, or I can read 2, or I can read 3. But what does or mean? Or means that I add. So if I go to write my combinations, I have 38 plays to choose from. I can read none. Or I have 38 plays to choose from. I can choose 1. Or I have 38, choose 2. Or 38, choose 3. And yes, you can enter all of that in your calculator and you'll come up with your answer. So to speed things up, I'm going to kind of stop doing the examples on the calculator. I think you get the gist of it, and I'll just keep working forward. So this was our important add. Here's another one that we want to take a look at. We looked at most. Now let's look at an example with at least. So let's go ahead and do this red one. It says, during playoffs, the girls basketball team is scheduled to play 5 games. Okay, so I'm going to underline what is important to me. Here's my 5, and here's my games. You want to attend at least 3 of those home games. How many different combinations of games can you attend? So at least, meaning I want to go to 3 games, or I want to go to 4 games, or I want to go to 5 games. So the way I would set this up is if I have 5 games to choose from, I have 5 games total, I'm going to choose to go to 3 of them, at least 3, or, not the or, meaning plus, 5, I'm going to choose to go to 4, or 5, I'm going to choose to go over all 5 of them. You punch that into your calculator and you're done. So then we covered Pascal's triangle. For Pascal's triangle, there's a simple pattern to kind of learn this. We start with 1 and then 1, 1. Well, if I go 1, 2, 3, and then I'm going to do one more, I get 1, 3, 3, 1. What is it that we are doing here? In fact, all of these are going to be 1s, and all on the other side, we're also going to have 1s. What we are doing is we're taking the 2 numbers above and adding those together to get the 1 in the bottom. So 1 plus 2 is 3. 1 plus 2 is 3. If I do another one of these lines, I'm going to group those numbers on top and then write them in. So I get 1 plus 3 is 4. This is 6, and this is 4. One more line. We get 5, 10, 10, 5. Well, you can actually Google this, search this, and you can find a lot of Pascal triangles that you can actually copy this down. I gave you in class a little slip that you're allowed to use for your quizzes as well. Here it is, Pascal's triangle in all of its glory. Now, the way you use this, let's say I wanted to get 8, choose 5. So something to remember is that we're going to count from 0. We start from 0. So this is our 0 row. This is our first row. Second, third, fourth, so on, all the way down to the 10th row. To kind of understand how that works, here's n is equal to 1, so that's 1. Here's 2, 3, 4, 5, 6, 7, 8, 9, 10. So these numbers is a little pattern that it develops. So the way we want to work this is we want to go to the 8th row. So again, starting at 0, we go 0, 1, 2, 3, 4, 5, 6, 7, 8. And we want to go to the 5th column. We start with 0. 0, 1, 2, 3, 4, 5. So 8 choose 56. I'm sorry, 8 choose 5 gives me 56 ordered combinations. Let's try one more. We'll go 7 choose 3. So I'm going to go down with my 7th row. 0, 1, 2, 3, 4, 5, 6, 7. I'm going to look at the 3rd column. 0, 1, 2, 3. So that's equal to 35. This makes it a bit easier for us to evaluate. Now, Pascal's triangle is important because when it comes to binomial or using the binomial expansion theorem or the binomial theorem, we're able to calculate things a lot quicker. So in the binomial theorem, there's a lot of fancy math going up on top over here by the definition. All I really care about is this formula or this little algorithm. We have n choose r times a. We're going to subtract our two sub-indexes, n minus r times b to the r power. So if we're looking at this example, just to kind of set things in motion, what is my a value for here? Well, we get a. What is my b value? Well, that's just b. And what is my n value? My n value is going to be my exponent. So my n value is 4. Now I have everything I need to set it up in this format. So again, we start with 0. So if we start with 0, I want all 4 iterations of this binomial. Now the binomial theorem is used to expand polynomials. So before we used to multiply a times b times the quantity of a plus b times the quantity of a plus b times the quantity of a plus b. So instead of doing that FOIL method nightmare, we can actually use the expansion or binomial theorem to kind of clear everything out. I'm sorry, to kind of multiply it all out. So here we go. We have to start with 0. So 0, choose, I'm sorry, that's not right. So we start with n is 4. So 4, choose 0 of our a value is just a. 4 minus 0, which is 4, and my b is going to be 0. Plus my second iteration, 4, choose 1, a to the third power. I'm subtracting these two to get that 3, b to the first. Plus 4, choose 2, a to the second power, b to the second power. Plus 4, choose 3, a to the first, b to the third. Plus I'm going to go down here, plus 4, choose 4, a 0, b to the fourth power. Yeah. So then we can evaluate that out. But to kind of show you a better example of how to work this, let's look at example 4. So again, we know for a fact, or I've told you guys that we're dealing with n choose r of a n minus r, b to the r power. So this is where things might get a little confusing. What is my a value here? Well, my a value here is x squared. My b value here is y, and my n is going to be 3. I'm going to just plug things in. Again, we have to start with the 0 iteration. So we have 0. I'm going to choose, sorry, wrong again. Oh boy. There you go. So we have n is equal to 4. I'm sorry, n is equal to 3. So we have 3. I'm going to choose 0. My a value is going to stay as x squared. That's never going to change. What is going to change is its power. It's 3 minus 0. So we actually have 3 minus 0 is 3. My b value will never change. That's y. And my exponent to that is going to be my 0. So 0, my r value. So then I'm going to add. Let's get adding black. There we go. And I'm going to do the second iteration. So I get 3, choose 1. My a never changes. 3 minus 1 gives me a 2. And I get y to the first power. This sub-index, this r, will always match the power of my b value. So now I'm going to go next iteration. I get 3, choose 2. My x value remains exactly the same. And I'm going to 3 minus 1 is the first power. My y has a power of 2. And my last iteration is 3, choose 3. I get x squared. The power of 3 minus 3 is just 0. Y to the third. So we're going to keep going starting from 0 until we hit our n value. So now to kind of evaluate, we can either evaluate 3, choose 0 in our calculators, or we can use Pascal's triangle. If I go back to Pascal's triangle, my third row, n is 0, 1, 2, 3, is 1, 3, 3, 1. So I'm going to use that pattern, Pascal's pattern, triangle, to evaluate or finish evaluating my binomial. So again, we have that it's going to be 1, 3, 3. So we said 1, 3, 3, 1 was from Pascal. So 3 choose 0 is just going to be 1. If we multiply power to power, we have to multiply powers, so we get x to the 6th power. Y to the 0 power is just going to be 1. So again, we're multiplying all that out. Plus, here's my plus, here's my plus, and here's my plus. So I'm going to add all of these terms together. So 3 choose 1 is just, once we're done with this one, 3 choose 1 is going to be 3. 3 choose 2 is going to be 3, that's up here, and then 3 choose 1 is going to be 1. So we can actually just write that in already. So the hard part is just kind of doing the power to power rule. It's just x to the 4th power, y to the 1st. X to the 2nd power, y squared. Anything to the 0 power is 1, so we get times 1, y cubed. If we simplify this out, 1 times 1 is 1, x to the 6th power, we get x to the 6th power plus 3x4y plus 3x squared of y squared plus y cubed. And that is our expanded binomial. So instead of doing box methods or a bunch of FOIL, we can actually evaluate this binomial or polynomial in 2 lines. 1, 2, and then simplify it, so technically 3. So the last thing I want to cover is to find the coefficient of x to the 4th. Now, instead of doing the expansion of 10 iterations, I just want to find what x to the 4th, or the leading coefficient, is. So to remind you guys what a coefficient is, if I had 25x squared, what is my coefficient for x squared? Well, that's just the number in front. It's 25. So with that said, let's get started. Again, I'm going to want to use n choose r, a of n minus r times b to the r. What is my a value here? Right. What is my b value? Okay. And what is my n value? 10. So we're going to use all of these. Everything we need is set for us. We just have to plug into the top formula. So let's go ahead and plug in. We get n, choose, I don't know what r is yet, so I'm going to leave that blank. My a value is going to be 3x. So I get 3x of 10 minus, again, I don't know what my r value is. So I'm going to leave that blank. And my b is going to be 2, and my r value is blank. Well, if I leave it as is, I have 3x to the 10th power. I'm looking for x to the 4th. So what do I have to subtract from 10 to get a 4? Well, I have to subtract 6. That means that r is equal to 6. This will be 6, and this will be 6. If I do that, I can just simplify this further to have 10 choose 6 of 3x to the 4th power of 2 to the 6th power. So what is 10 choose 6? If we go back to our Pascal triangle, the 10th line is here. We're going to choose 6. 0, 1, 2, 3, 4, 5, 6. That's going to be 210. So we're going to go back down. We're going to use that 10 choose 6 is 210. So you can use Pascal's triangle or your calculator. I'm fine either way. And you're going to multiply that, distribute the power. So you get 3 to the 4th times x to the 4th. Then 2 to the 6th power. Well, that's just 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 32. So now we just want to multiply these numbers out. So, or to kind of clean things up a little bit more, we have 310 times 3 to the 4th power. I'm going to use my calculator. I think it's 81. Yes, it is. 81 times 32. Oh, I'm sorry, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, 64. So that should have been 64. There we go. All right, much better. So times 64 to the, or times x to the fourth. So then I just multiply these numbers out. So I get 210 times 81 times, I'm sorry, 210 times 81 times 64. We get, or I'm sorry, right here, we get 88640. So we get 1,088,640 is our leading coefficient for x to the fourth power. Pretty big number. This makes it that much easier. Imagine multiplying this 10 times with a box method or FOIL. It would take forever. This actually saves us a lot of time. That's it, guys. I had an exit clip for you guys. You guys had a group exam. And here are the assignments. Again, if you scored red on your quiz, you do those problems. Yellow, you do those problems. And green, you do those. Hope this helped, guys. I'll upload this soon. Bye-bye. Till next time.